All right, hello everyone. My name is Elise, and I'm a first-year PhD student from the University of Amsterdam, working on radio-emitting M-stars, which are good candidates for star-planet interactions, specifically star-planet magnetic interactions. Now, the interest in these types of interactions started out when we observed bright radio emission coming from Jupiter and Io. So Rob already explained this, but I'll explain it briefly again. What's happening here is Io orbiting around Jupiter. It interacts magnetically with Jupiter's magnetosphere, and so charged particles are accelerated along the magnetic field lines to the planet's surface, where through the electron-cyclotron Maser instability, the ECM instability, we ultimately end up with a radio emission cone. Now, if we are, instead of talking about a moon orbiting a planet, we now talk about a planet orbiting around a star, we are effectively scaling up this system. And so we would expect that bright radio emission, such as observed in Jupiter and Io, should also arise in star-planet systems. And as Rob mentioned as well, this is not the only way in which we would expect radio emission to occur in exoplanet systems. So on top of this star-planet interaction scenario that I just described, we can also expect radio emission to occur from a planet's magnetosphere itself through magnetospheric interactions. So what happens here is that the magnetic field of the planet is impinged by a stellar wind, and so the magnetic field lines from the day side get reshaped back into the night side, where the magnetic field lines can then reconnect, and this as well creates charged particles, ultimately producing a radio emission cone. So if you can also note that these two different radio emission mechanisms can occur in very different exoplanet systems, with the SPI scenario occurring in close-in planet systems and magnetospheric interactions being more likely for massive, far-out planets. So then if radio emission occurs in exoplanet systems and we were to detect that radio emission, does that mean that we could have a potential new way of detecting exoplanets? I find this a very exciting possibility just by itself, but what would be particularly exciting about this detection mechanism is that it would allow us to constrain the magnetic environment of the system. As Rob described in his talk as well, this will allow us to answer numerous questions, not just about the magnetic environments, but also concerning questions like the habitability of the planet. For this reason, a lot of people have been trying to look for these kind of radio emission star-planet interactions, but unfortunately, currently there are no robust detections of magnetic SPI. Why is that? Well, one of the main challenges in detecting this kind of SPI, this kind of radio emission, is because we're talking about very low frequencies of radio emission. And so we're talking about less than roughly 150 megahertz, and many of our radio facilities today just have not been sensitive to these frequencies. But that's starting to change now with the advent of LOFAR, the low-frequency array. It operates in megahertz frequencies of 10 to 240 megahertz, and so it is for the first time reaching frequencies sensitive to SPI. And indeed, it has found 19 radio-emitting M-stars. So the question that we are now trying to answer is, okay, well, what is causing this radio emission, and could it indeed be because of magnetic SPI? What we are looking for when we are trying to answer this question is we're looking for repeated radio emission. Because we're talking about orbiting system, we would expect some type of periodicity. To answer that question, or to look for that repeated radio emissions, we then continue monitoring with LOFAR, but what's difficult about radio, this type of detection, is we've never done it before. So in the radio, we're effectively kind of flying blind. We don't really know what we're doing yet. And that's where RV observations can come in very useful, because the RV technique, it's a very established technique, and so if you can use that technique to confirm planets compatible with SPI, this will help us inform our radio observations and hopefully open up this new field of exoplanets. This combined observations of both radio and RV observations are together put into a survey which we call the Radio Exoplanet, or the TREX survey, and this survey is then following up all of these radio-emitting M-stars. The RV observations, we are taking those with the Habitable Zone Planet Finder, or HPF, which is on the 10-meter Hobby Eberly telescope. It has a high resolution of 55,000 and a wavelength range of 110 to 1280 nanometers, covering the near infrared. And so together, this allows us to gain a very high position on these cool M stars. So what have we found? So far, the HPF observations have shown that the sample varies in multiplicity and in activity. And in order to illustrate that, I show here all of our radio-emitting M stars on top of a HR diagram with the main sequence plotted in the background. And if we first of all distinguish between the single and the multiple systems, the HR diagram then looks like this. Some of these multiples were far out binaries that were already that we found in the literature, basically. But some of these were revealed by HPF to be spectroscopic binaries. So here we see the broadening functions, and we see that they have multiple velocity components, with one system even showing 3 velocity components, and so this pointing to a triple system. We can then also make a distinction between the active and the inactive stars in our sample, with now the inactive singles shown in red. And it's these inactive, slowly rotating stars which are prime targets for SPI, because in this case, it cannot be flares or activity of the star producing this radio emission. And it seems that then the SPI scenario is the main way in which radio emission can be produced. And so currently, we are searching for planetary companions around these SPI targets. And for the purpose of this talk, I would like to highlight these 2 targets, GJ1151 and GJ625, starting with GJ1151. So GJ1151 was the first ever quiescent M star observed to produce radio emission. And of course, we weren't the only people thinking, okay, maybe the RV technique would be a good way to follow up the system. So several teams have been following up this system. And so have they found a planet around this star? Indeed, they have. So here we see the radial velocity curve. We see a roughly 400-day periodic signal, as well as a long-term RV curvature. And this 400-day periodic signature is produced by a sub-Neptune planet. So we have now found an SPI target with an orbiting planet. Great, are we detecting SPI here? Well, don't get too excited yet, because this sub-Neptune is not consistent with SPI. It's too far out to be magnetically interacting with its host star. But as I mentioned, we also have a long-term RV curvature pointing to a further out, more massive companion, which is kind of a rare thing in itself. And we're also talking about a radio-emitting target, which is also a rare thing. So could those 2 things be connected? And is an outer massive companion the source of the radio emission? Well, to answer this question, we have an upcoming JWST NIRCam observation to further characterize this distant companion. Here on the left, we illustrate what this would do to, or what we can tell about this companion with the JWST observations. We see that the companion mass and the semi-major axis with just the RV observations doesn't really tell us much. But if we then include the JWST observations, we can see that we can constrain this parameter space much more closely. And so we hope to answer the question of, well, if this is this a brown dwarf or a giant planet? Because if it is, then this would be more consistent with a magnetospheric interaction scenario. So moving on now from GJ1151 to GJ65, this target as well has a previously confirmed orbiting planet, and this time at a period of 14.63 days. So you might already be questioning, okay, well, is this then consistent with the SPI scenario? To give a bit of an example, there have been modeling done on AU-MIC, and in this case, for AU-MIC, if we are assuming weak stellar winds, there is a planet at an orbit of roughly 19 days that could be consistent with SPI. So 19 days, that's more than our 14.6 days, and so 14.6 days, it doesn't sound too crazy. However, if we really want to quantify the answer to this question, we would need to have the global stellar magnetic field measurements, which we currently, well, as far as I'm aware, there are no measurements made. But if anyone is aware of these measurements having been done or are doing these observations, we would be very eager to talk. In the meantime, we have updated the RV analysis. So since the Harps North observations have been done, publishing this 14.6-day period, new RVs have been obtained with HIRIS, Carmenus, HPF, and NUID. And so if we combined all these new RV publications together, we see that we can improve the period uncertainties by a factor of roughly 3. And this will greatly help us in the upcoming radio follow-up. So these are just 2 targets that I wanted to highlight, but all of the other targets in our sample, we're still following these up, and we are still doing analysis on all of these targets. And also, this sample is only drawn from 20% of the northern sky, but LOFR is surveying the entire northern hemisphere. And so in the near future, we can expect 60 to 80 more radio-emitting targets. And also in the southern hemisphere, there is, of course, the square kilometer array that's upcoming. And so we can expect many more targets in the near future. That brings me to my summary slide. Radio telescopes have uncovered radio emission from 19 nearby M-stars. The T-REX survey is probing for planets compatible with SPI around this sample. So far, we have found that radio-emitting M-stars vary in stellar activity levels and in multiplicity. And in the near future, we can expect more radio detections from LOFR and the SKA.
Last pencil. Let's go to, are you guys finished? Yeah. Oh, he hasn't asked a question, so let's go to that one.
University of Queensland. If you go back to GJ 1121, was it 11? You got the. Does the JWST, if you can observe the companion directly with NIRCam, does that actually characterize the SPI? Like, can you get a spectrum and actually observe evidence of the SPI directly?
Sorry, can you repeat the question?
If you can observe the companion with JWST NIRCam, can you like directly characterize the SPI, the star-planet interaction, like through evidence of aurora or something like that?
So you're saying, would this be conclusive evidence of SPI?
Yeah.
Well, in this case, we would be, since it's a far out companion, we would not be thinking about SPI because that really requires a closing planet. Right. In this case, we would really be talking about magnetospheric interactions. And no, this would definitely not be okay, we have found complete evidence of this happening. We would definitely need further observations and modeling to really confirm that further.
Thank you.
Okay. Over here.
I'm wondering, Jim Davenport, University of Washington. I'm wondering, you have supposedly inactive stars. Do you have any detection of radio variability from these? Or is it just, we can detect radio emission, but we don't have any time component to it yet?
Yeah, so in these low frequencies at least, so far for all these targets, we've only seen one radio observation, and it's a long period duration. So that's what's different from regular variability. It's a long duration component. But yeah, we've only, like I said, only seen it once. That's why we're really eager for these repeated radio observations.
Let's go over here in black, please.
Okay, cool talk, thank you. Maybe this is a stupid question, but if you are looking for a giant planet in a tight orbit around an M dwarf, is it sort of biasing yourself to look at like inactive stars because they might induce activity in that case? So wouldn't you maybe want to look at the active stars?
The problem with the active stars is that you can also produce radio emission through plasma emission, so through flares. This would create a similar coherent radio emission. So that's why we're really focusing on the inactive ones, because then you don't have that question of, okay, we see radio emission, but it could be via 2 different ways. So yeah, that's our motivation, at least, for going for these inactive ones, because you already rule out one of the 2 scenarios.
There are more questions, but if you have them, please come find the speakers over lunch. And if I owe you a pencil, come here. And let's give another round of applause.